Okay, integrals. I'm so excited. I'm actually starting right here. Okay, this is for me page 10. Okay, integration. Okay, integration is the antiderivative. It's the opposite of derivatives. So, if you wanted to work backwards from the derivative, or if you had like the derivative of something you're trying to get back to the base function, you would do an integrate. You would integrate it to figure it out. Derivative gives us the slope of a function, right? We figured that out in the last part. However, the integral is actually the opposite, and the opposite of the slope of the function is the area between function and x-axis. Okay, and it can be negative or positive, right? We've seen negative and positive area before. Okay, so now it can be the integral can be negative or positive. Here's how we do it, okay? And I really like the way that it's taught because, in my opinion, it makes a lot of sense to me, okay? Okay, the first thing is that what happens is you split the x-axis, okay, into tiny intervals, okay, which we call dx, okay, which we call dx, okay. You multiply, okay, each dx, okay, by the function's value, okay, above that dx. Okay, so what we're doing, right? So you can kind of see right here what we're doing is we've taken the x-axis and split it into these tiny little intervals dx, okay, and we're multiplying that dx, that the length of that interval, by the function's value above that dx, which is going to be like this, right? Oh, you see what I'm making? Okay. See what I'm making right there? I just made a rectangle. So I'm really just getting the area right here, right? Okay. So this gives us a tiny area. Okay, so what we're doing is we're getting a tiny bit of the area under the function, but as you can see in the final image right here, it's not just one rectangle, it's a bunch of rectangles here. Okay, it's a bunch of rectangles. Okay, and what you're then going to do, right? So you should notice, right, that the value of the function above that dx times dx gives us the tiny area. Okay? This right here, this part right here is your height. Okay? This part right here is your width. Okay? So you're multiplying your height by your width to get the tiny area. Okay? Then what you're going to do is you're going to add up all the areas to get the total area under the function. Okay? And that is the process of the integral. That's what the integral is. Okay? You're going to see, oh, what am I doing right now? Scratch that out. You're going to see that the area is simply equal to the integral, and that's the symbol for the integral. Okay? F of x times dx. Okay? That's what it is, right? The integral, what it's doing, in essence, is adding up, okay, all pieces. Okay? And then f of x is the height, dx is the width. You're just taking all those tiny little areas and adding them up. Now, you can add bounds to the integral. Okay? If you add bounds to the integral, then you only want the area under a certain segment. That's perfectly fine. You can do that, okay? But if it doesn't have bounds, then it's indefinite integral, okay? It kind of gives you more of like a general look at it, okay? You might notice that there's some pieces that kind of go over, like little over approximations. There's some that go under, but it should all end up canceling out. I think those extraneous pieces end up kind of working out to where it gives you the solution for that. Okay. Okay. There's two types of integrals that you need to know. Two types of integrals: an indefinite and a definite integral. An indefinite integral is the antiderivative of a function. When we use the indefinite integral, we were pretty much just using it to get the function, the base. If the function we're working with is the derivative of something, we want to get that original something, right? It's the antiderivative of a function. Okay. Plus c. And what is c? C is the constant of integration. Constant of integration. Okay. Okay. So what this would look like, right? What this would look like. So why do we say the plus c? Because you know that when you take the derivative, right? If it's just a constant value, if it's a constant like 5 or something, well then it gets knocked out when you do the derivative. So when you go backwards, when you take the antiderivative, you actually have to account for the fact that you might have lost something, and therefore you now need to pick that back up by using this plus c, because in physics, typically we'll know what plus c is. We just plug in the initial conditions, right? Okay. Definite integrals, okay, has bounds, okay, which is the starting and ending point. Starting and ending point, okay? And it's notated as the integral from a to b. Okay, you'll see a on the bottom, b on the bottom. This is the lower bound, upper bound. Okay, where a is starting and b is ending. Okay, both are x values on function. Okay, so both of them are x values on the function. Now, the fundamental theorem of calculus gives us that if we're trying to solve a definite integral, a definite one that has bounds, then the way that you would solve it is pretty easy. All you would have to do is, if you have the integral right here, here's your bounds, b, a, okay, of f of x dx, okay. If we're trying to do that, then the antiderivative of this, or sorry, the integral, the definite integral for this, okay, is given as the function with b plugged in minus the function with a plugged in. Not the function that you're taking the integral of, but rather the integral with b plugged in. A and b are the bounds, okay, and f of x is the antiderivative, capital F of x, antiderivative, okay? Okay, so basically what it's saying, right, is that to figure out the definite integral of something, right, you take the integral of the function and then you plug b into the x and then subtract it from the same function but with a plugged in for the x. And it's a lot easier to see in practice, and I'll show you how that works, okay? Okay, and I really quickly also, before I continue, I do want to really, really quickly show you the general power rule for integrals. Okay, the general power rule for integrals is pretty straightforward. All you have to do is if you have a function that's like c times x to the n, okay, dx, okay, what it would be is you would set that equal to c over n plus 1, okay, times x to the n plus 1, okay. And if it's indefinite, then you would have to do the plus c. I'm just going to leave the plus c out of it for right now, just because this is kind of more of a general form. So that's more of a general form to getting the integral of that, okay? To taking the integral with like a power rule, okay? I'll show you how to do u substitution here in just a second, okay? Okay, so to evaluate this, okay, there's two steps. First, you have to take the integral, and then you need to apply the bounds. Okay, so I'm going to take the integral of the function first. Okay, so that's what I'm going to do. Here's what I'm going to do. I'm going to leave some space. So the first thing I'm going to do is I'm going to write all the x's in here, and I'm going to then increase their power by 1. Okay? You notice that 7 really has x to the 0 attached to it. So it would be x to the 1. So this is going to be x to the third here. Okay? Plus x to the second. Okay? Minus x. And then the bounds are from 4 to 16. Okay? Okay, so now what I'm going to do, now all I'm going to do is I'm just going to plug in what needs to be in front of the x's to make it so that what constants do I need to put in front of all the x's to give me a such that when I take the derivative of this function, it gives me this, right? Okay, so the easiest way to do that, right, is to think, okay, well, what times 3 is going to give me negative 1/4, right? Because when I bring the 3 down, I need to be able to cancel, because I'm going to have to bring the 3 down, and it should end up with negative 1/4 in front of this x squared, right? Okay, so the easiest way to do that, right, is to follow the power rule up here. So I would take my negative 1/4 and divide it by the 3, okay? And when I do that, I end up getting 1 over 12, negative 1 over 12, okay? For the second one, it's a lot easier when you do whole numbers, right? I'm going to do 4 over the 2, okay? And that gives me 2. Okay, and for the last one, okay, it's just going to be 7 because there is no, I mean, right, it would be 7 over 1, which would just be 7, right? And then do you notice that if you take the derivative of this function inside the brackets, it gives you this function right here on the integral? That's what you're looking for. That's ultimately what your goal is to get, okay? Okay, so now what I'm going to do is, now I have not finished yet because I need to apply my bounds to it. This is going to look really weird. It's going to be a really messy problem, okay? So now I'm going to apply my bounds to it. This is going to be negative 1/12 times 16 cubed. So you see that I'm taking 16 and replacing all the x's in here with 16, okay? Plus 2 times 16 squared minus 7 times 16. Okay? That's this capital F times F of B. Now I need to do the capital F of A. So it's the same thing, but instead of all the 16s in here, I'm going to replace them with 4s. So I'm going to get negative 1 over 12 times 4 cubed plus 2 times 4 squared minus 7 times 4. And the answer to this, if you punch all this in your calculator, because that's a really long problem, just punch that in your calculator, you would end up getting the integral, which would end up being 60. That's the area under the function. And you can see that here because the function is shown to the left here. You're taking the area from this point. These are your bounds. Okay? You've got a bunch of positive area up here. And then you have a tiny bit of negative area here, and it tells you what those values are. You would do the positive area 66.666, and then the negative area 66.666. You would subtract them because the negative area detracts from the positive area, and you end up with 60. Okay? Okay. For the next part, okay, to find the indefinite integrals, okay, this is very, very important. When you're doing indefinite integrals, you need to remember, you must remember plus C. Do not forget the plus C. Do not forget plus C. Don't forget plus C. If you forget plus C, you're going to screw yourself out of a lot of things, okay? You're going to screw yourself out of a lot of points here, okay? Okay, let's take the integral of the first one, x to the third, okay? So getting x to the third, okay, the integral of that is pretty straightforward. So what we're going to do is we're just going to do the constant in front of it over, so the constant in front of it is 1, over the exponent plus 1 times x to the exponent plus 1. Oh, look at that. That's the integral. That's the integral, right? You notice when you take the derivative of this, it gives you x to the third, right? And we cannot forget our plus c. Okay, you have to put a plus c at the end because you don't know if you've lost any terms from when you took when we took the derivative to get x to the third. Okay. Okay. What about the next one? Well, this one. Okay. All we're gonna do for this one is again. So this is x to the third. Okay. Plus x squared plus x to the first power. Oh, and plus c. I'm just gonna write the plus c right in there. Okay. So then all we got to do is plug in values that make it so that when we take the derivative, it gives us that. Or just divide the constants in front of the x's by their new exponents. So this would be just 2 over 3, right? Because when you bring the 3 in front, then it cancels out and you're left with 2. Boom, we're great, okay? Right here, this is just going to be 3 over 2. You do not need to simplify in this class. You can leave it like this. That's perfectly fine. I'd rather you do that, actually. And this should just be 4. Boom, we just took the integral. Are you proud of yourself? Okay. This last problem, this third one right here is weird because you need to write this in a form that makes best sense for you. Okay. I'm going to do x to the 1/2 plus x squared plus x to the negative 2. That makes sense to me. I'm fine with that. Okay. Now I can take the integral of that really easily. Okay. Wait, now I can take the integral of this, really, really easily. Okay? So first off, right, I'm going to write my x's with their exponents incremented by 1. Okay? So this is going to be 3 over 2. Okay? Plus x to the third plus x to the negative 1 plus c. Okay. Okay, now I just got to figure out what numbers go in those places. Okay. Well, we don't have any constant here. We don't have any constant here. So let's just so we would have to divide, it would be 1 divided by the new exponent, which would actually just be 2 over 3. Okay. For the middle one, this is just going to be 1 over 3. And for the last one, okay, that's just going to be negative 1 over, or I guess it would just be negative 1, right? So we're not adding anymore, we're subtracting just that, okay? And that's it. That's the whole integral right there, okay? Okay, now here's where things get tricky. I have to teach you something called U substitution. I don't know realistically how often you're going to use it in physics before you learn it in calculus, but I'm going to briefly teach it to you really quickly. U substitution, okay, or U sub, is reverse chain rule. Okay? You have to start by choosing, okay, internal function, okay? Choose the internal function to make u, then find du. Okay, let me tell you how that's going to work. Okay, then you then substitute and solve. Then solve. Okay, so here's what I'm going to do. I'm going to choose my internal function here. Okay, so here's my external function, and here's my internal function. Okay, the 3x. Okay, so since that's my internal function, I'm going to make that u. U will be equal to 3x. Okay. So when we do U substitution, we're literally taking our internal function, we're just making it U. We're going to make it easy on ourselves. We're going to make it U. Okay, that's how U substitution works. Okay, it could be J substitution, it could be M substitution, doesn't matter, whatever works for you. But traditionally we use U substitution. And then we need to define a function, then we need to define du, which is the derivative of U. Okay, the derivative of U is just 3. Oh, sorry. Yeah, it should just be 3 dx. And why does dx? Dx is like the derivative of x. Okay? So 3dx, okay? Um, so then what we can do now is we can make so what we want to do, right, is instead of using everything in terms of x, we want everything to be in terms of du or u or du, right? So in doing so, okay, you notice that our du is 3dx, but we actually have 12dx out here, right? So in order for us to get it so that inside the integral, we want there to be 3dx, but we currently have, if you take out the sign part, we currently have 12dx, right? Okay, so then if I factor the 12 out into 4 and 3, and I take the 4 out of the integral, which you can do, okay, then I end up getting 4 integral of sine and 3x, by the way. Okay, 3x, by the way, is um, I'm just going to replace it for u here. So it's going to be sine of u du. Okay. Then you just take the integral like normal. This is so much easier to take the integral of because now you don't have to worry too much about chain rule. You're just taking the integral of sine. Okay. And the integral of sine is negative cosine. Okay. So I would end up getting negative 4 cosine u. Okay, plus c. Now here's the issue. I then need to substitute the u back in. So this gives you negative 4 cosine 3x plus c. Okay? Okay, to get e to the 2x, again, take a look at it. We have we have an interior function and exterior function. My exterior function is e to the 2x. My interior is just going to be the 2x. Okay, so in doing that, I'm going to say that u is equal to 2x, and then the derivative of that du is going to be just 2 dx. Okay. Oh, do you notice that now? So it says I need 2 dx, but I don't have any dx's. So what I can just do is I can multiply the whole thing by 1/2 at the end. Okay, because I need, this is actually just 1/2. So it's actually going to be 1/2 of the du, right? If du is 2 dx and I don't have a second dx to give, I just do half of du, and then um, that would have to get represented in our integral now. So when I do that, right, when I rewrite it like this, okay, I'm going to get, let me do this in orange, or let me make a little wall here so that I don't, confuse you with my writing. Okay. So when I plug everything back in, it's actually 1/2. Okay. It's actually 1/2 of dx. Okay. Or 1/2 of the integral. 1/2 integral e to the, what is it, 2x. I'm just going to rewrite it as u. Okay. du. Okay, integral of e to the u is just e to the u. So this is going to be 1/2 e to the u plus c. And then you replace the u. It's 1/2 e to the 2x plus c. That's it. Okay. One thing that you should notice, and I have this written here, and is if y is equal to e to the 2x, then the first derivative of y is going to be 2 times e to the 2x. Okay. The second derivative of that is going to be 4e to the 2x, because you notice that you're bringing down the derivative of that. You're kind of using the chain rule here. Okay. And then the third derivative of that is going to be 8 e to the 2x. You notice it's just getting multiplied by 2 each time. Okay, this last problem right here, again, you can use u substitution to solve this one. Okay, so I'm actually going to regard the interior function as 2 plus 4x and the exterior to be this whole thing. Okay. Okay. So in this one, right, I'm going to define, so I've defined u as being 2 plus 4x. So then du is going to be 4 dx. Okay? I can separate 20 into being 4 and 5. So I'm actually going to take the 4 out, and the 5 is going to come out into the front. Okay, because I need 4 dx. 4 dx is just going to turn into du. So this is going to end up looking, like 5 integral of du over u. Okay. And then you should notice, okay, this is 1 over u times du. The integral of that is just going to be 5 log natural of u plus c, right? And then make sure you substitute the u back in, and you end up getting 5 times natural log of 2 plus 4x, okay, plus c. And you can, and the reason, oh, and actually, so these right here should be absolute valued. And the reason they're absolute valued is because um, abs value, because ln of x undefined for negative numbers. Okay. Okay, that's use substitution. Okay, I don't, again, like I said, I don't know how frequently you're going to use it, but it will definitely help you to know that, at least if at the very least in your calculus class. Okay, and the very last thing I need to talk about is these new relationships. So why am I teaching you all this calculus? Because it connects strictly to physics, right? It connects straight up to physics. Position and velocity have a new relationship. Okay, you know that velocity. Okay, velocity is the derivative, okay, of position, okay, with respect to time. In other words, v is equal to dx over dt, okay? You should also understand that the change in position is going to be equal to the integral of velocity with respect to time. Okay? That's change in position, not position, but change in position, okay? And then another relationship here between velocity and acceleration is that acceleration, okay, is the derivative, okay, of velocity, okay, with respect to time, okay? And that's a equals dx over, or sorry, dv over dt, okay? dv over dt. And then the velocity, another relationship here would be that the change in velocity should be the integral of a times dt, okay? There you go. Integrals. Have fun. Great. Cool. Girl boss it up. Have fun. Slay.